I'm going to start the video for this section by looking at the central limit theorem. And what it says, if we take samples of the same size, if we look at a bunch of different samples of the same size, and there's at least 30 things in the sample. And we could look at a measurement, a statistic from that sample, let's say the mean. If we looked at the means from all the different samples, we could see how all those means are distributed. And what the central limit theorem tells us is that if the sample size is at least 30, we're going to end up getting a normal distribution for our sample means. It tells us even more than that. It tells us that the distribution of our sample means, the actual mean of that is going to be equal to the population mean. And then so we expect most of our samples to have means really close to the population mean, and the further away we get from that population mean, we'll have less and less samples that have a mean that's really far away from the population mean. It also tells us how to calculate the standard deviation, and I'll go into more of that later. And one more thing it says is, I said we needed size at least 30 for our sample. Well, that works then for any population at all. But if we knew our original population was normally distributed, then our distribution of our sample means automatically, no matter what sample size, will also be normally distributed. So it could be sample size of anything. It doesn't have to be at least 30. It could be 4 or 10 or any number at all. But let's think of this with just some real context here. Let's say the average height of men is 5'10". And so if I had every person in class go out and survey 100 men, 100 guys, and find the average, the mean from their sample of 100, most of our means are going to come back really close to 5'10". Now there may be a few people who get a sample that had some unusually tall people in it, so their sample mean will be a little further out in the tail. Some people may have a sample with some short people in it, so their average of their 100 people may be really far out here in the left-hand tail. But if we looked at the distribution of every possible sample of 100 men, and we looked at the mean of all those different samples, it'd be a normal distribution, and the average, the mean of all those samples would actually be 5'10". That's what we'd expect to get most often, is our sample is going to be right around 5'10". And so to actually start looking at the homework here, the first one, if we just had a population that only had 5 things in it. All right, so first we want to see what is the mean and the standard deviation of that population. So in Excel, you can use the average formula to find the mean for the entire population, and then you can do standard deviation dot p because we have the entire population. So use the dot p for the standard deviation of the entire population. And now in this example, we're looking for samples of size 2. So we want to actually list out all the possible samples where you're selecting any 2 things from this population. So you can see there's going to be quite a few. And it could be the same exact number selected twice. Like here, this sample has 547 and 547. And for each of these samples, we want to find the mean of it. So just average the 2 numbers. So that particular sample has an average or a mean of 547. If the sample has 2 different numbers, add them together, divide by 2 to get the mean of each sample. So all those means, we want to see what the distribution is of all those means. That's the sampling distribution of the mean. So you want to look at the means here of every single different sample. You probably want to type them in Excel or something. And then what you want to do is you want to take the average of all those means, because that's the mean of our distribution here. So these means, we want to average all those means to get the mean of our distribution. And if you do it right, this is what the central limit theorem says. You should get the same answer as the mean of the entire population. When you average the mean of every single sample, it's the same as the mean of the original data from the population. And so you can use that as a check. When you take the average of all your sample means, make sure it comes out to the same as the average of your original data. And you can use that to make sure that you didn't enter any of these sample means incorrectly. And then you want to find the standard deviation of all of your sample means. Now we have every single possible sample. So again, we have a population because we have every single possible sample of size 2. So do this standard dev dot p for population, and you'll get the standard deviation of your sample means. And going back to the central limit theorem, the formula for calculating the standard deviation of all of your sample means, it's going to be the population standard deviation and divide by the square root of your sample size. So just to show that, here I just look at every single possible sample mean and I did the standard deviation. I got this answer. I can also get it by looking at the population standard deviation and divide by the square root of 2, because that's what my sample size is. And when I do that, I get the same exact answer. So that's the formula for getting the standard deviation of your sample means. And so then just to summarize those results from the central limit theorem, the mean of all your samples is always equal to the population mean. And the bigger your sample size is, you're going to be dividing by a larger number here. So the bigger your sample size, the standard deviation of your sample means keeps getting smaller and smaller because you divide by a larger number. So that just means it's a normal distribution that's less spread out and more clustered around the mean, the larger your sample size is. So number 2 here, we have a population that it is already normally distributed. So it doesn't matter what our sample size is, we can use the central limit theorem. And essentially, we're going to try to find the mean of the sampling distribution and also the standard error or the standard deviation of the sampling distribution. So you're going to use what I just talked about here. The mean is going to be equal to the population mean, and based off your sample size, this is how you calculate the standard deviation of your sample means. Number 3, similar to number 2, you're going to use these formulas to calculate the mean and the standard deviation of the sample means. Number 4, you're going to find the mean and the standard deviation just like you did for 2 and 3. And let me talk a little bit now about how to find the correct graph that you need to do this for 2, 3, and 4. Just like any normal distribution, you need to have the mean right in the middle. So pick a graph with the mean in the middle. Then if you look at the graph, it's got the tick marks here, and these are indicating the standard deviations away. So 1, 2, 3 standard deviations away, it's saying is 136.6. And you can quickly check with a calculator that that's the correct graph. If you did your standard deviation here and multiply it by 3, so you have 3 standard deviations, it's that amount. So add that amount to your mean to see how much is 3 standard deviations above the mean. And you get that value 136.6. So you know that's the correct graph of your normal distribution with those characteristics. So number 5, we get into some story problems, and I'm going to show how to do these in Excel. And so for a certain job, it gives us the population mean for how much money that job makes. And it tells us we have a random sample of 39 people from that job. What's the probability that when we look at that sample of 39 people, that the mean for that sample is less than a certain value? And we're assuming what our population standard deviation is, that's given as well. And so here's the information from our problem. And since our sample size is 39, we know from the central limit theorem, since we have a sample size greater than 30, that the distribution of our mean is going to be normal. So it's going to be normal. The mean of the distribution is going to be the same as the population mean, and the standard deviation is going to be population standard deviation divided by square root of the sample size. So we have a normal distribution with these characteristics, and we're just trying to find if we randomly select a sample of size 39, so randomly select something from that distribution, what's the chances that we get a mean of 58,000 or less? And so enter your value you're looking for, and then your mean, your standard deviation, and true. And this gives you the left-hand probability. So getting a sample of 58,000 or anything smaller than that. So it's very unlikely. We would expect if we take samples of size 39 Very, very rarely are we going to get the average from that sample to be 58,000 or less. Number 6, another story problem. Identify the population mean, population standard deviation. And this time we're doing an in-between. Since the sample size is bigger than 30, again, we know our sampling distribution is going to be normal. And sampling distribution, the mean of it, it's the same as population mean. Calculate the sampling standard deviation. And then to do in between two values, remember you need to find the probability of being to the left of each of the values. So use that formula for each of the values. And then you take the larger one and subtract away the smaller one to get the probability of being in between. So for any in between, that subtraction basically is subtracting off the little bit to the left that you don't want. So that first value is the probability of being from that mark or anywhere to the left, and then you subtract the probability of being from that second mark to the left, and when you subtract off that bit, all you're left with is the chances of being in between the two values. Number 7 is more of the same, but this time we're finding the probability that the mean of our sample is greater than a certain value. So remember, for a greater than a right tail probability, you have to use 1 minus and then that formula in Excel. So that formula gives you the probability of being left of the mark. So 1 minus that then is the probability of being to the right of the mark. So whatever your value is, enter it, and the mean, standard deviation, true, and make sure you do 1 minus that to get the right-hand probability. Number 8 here shows us a little application of this material, and it goes into quality control. So in this situation, we have a lumber company that has bought a machine that automatically cuts lumber. And the sellers of the machine claim the machine is going to cut with a mean length and a certain standard deviation. And the people who bought the machine can do some quality control to see if it's really living up to those specifications. And so to do that, they take a sample of 43 boards and they find the mean of that entire sample. And so we're taking samples of size 43, so we know by the central limit theorem that our sampling distribution is going to be normal. We know what the mean of our sampling distribution is going to be, the same as the population mean, and we can calculate the sampling distribution standard deviation. Now, our question is, we're trying to do some quality control and see if the machine's really cutting boards that are really, really close to 72 inches like the manufacturer claimed. Our sample of 43 boards, when we took the average of those 43 boards, it came out to 72.11. Is that unusual or not? So we're going to use the fact that we have a normal distribution to test that. Now, this is above 72, so we want to see a right tail distribution then. We already got a sample above the mean. We want to know what's the chances of getting something that big or even bigger, so even further above, right-tailed. So we need to use this. If our sample would have came back to something like 70, which is already below the mean, then we would have done a left tail and seen what's the chances of getting that or something even further to the left. But we're above the mean, so we're going to see a right tail distribution. And when we plug in those values, plug in our mean, our standard deviation, do 1 minus for our right tail test, we get a very low probability that our sample would come back, a sample of size 43 would come back with this mean if these specifications are true. So we're starting now in quality control to think that it's probably unlikely that these are actually accurate. Any probability less than 5% is unusual, unlikely. Now, for the next part, we're seeing if it's going to be unusual to have one individual board from the population with that same size. And we are told that the population is normally distributed. So we're looking at the normal distribution here of our population. And again, we're trying to see a right-hand tail here. Is it unusual to get one board of that size, 72.11 or larger? And so plug that in. Make sure you use the population standard deviation, and you get this for the probability. And so that's way above 5%. It's not unusual to get one board of that size, but it would be very unusual if we took a sample of 43, and the average from all 43 of those boards was that size.